of you have seen parts of this study before. So I apologize for repetitions. There are many experts in Koornwinder theory here, so the following few slides are going to be a little bit of a repetition for some of you, which is great because they're rather crowded. But so, what I want to say today is I want to sort of compare the McDonald and Koornwinder pictures in terms of the eigenvalues equations and theory rules, and talk about the tools of the proofs that I'm going to provide for what I'll define in part 3. So, in particular, the universal solutions, which Therese has taught me about, actually, and duality and theory rules. And then I'm going to talk about something nobody's talked about here before, which is just taking the limit to the Q-Whittaker, so Q-Whittaker limit of all of this for each the algebra. And then I'm going to say that the resulting, so the pairing rules in the limit give me some sequence of commuting Hamiltonians, which are sort of quantum relativistic Soda Hamiltonians for the affine algebra G. And these are then I'm going to argue are the conserved quantities for some discrete evolution, and this discrete evolution is actually where I started my story, which is quantization of Q systems, which there are some experts in Q systems here as well. So essentially, from Koornwinder theory, you get so the spherical Deha, you get an understanding of how exactly the quantum Q system algebra is associated with spherical Deha. So that's, now you can go to sleep, that's the outline I will have. So this is a very crowded slide, but it's just to compare. So type AN is different from Koornwinder, so BC, and the affine algebras that I...
No, it is working.
Yeah, I don't see it. Yeah, maybe... Nicer? Yeah, I think so. Yeah, okay, so the type of affine algebras that I have accessible to me, so affine type AN in the McDonald side, for the BC type, under specialization of the Koornwinder parameters, the affine algebras with the affine root systems which are accessible to me are type BCD, untwisted, and then in the Katz notation, twisted A and D. And yeah, so the root systems, I just listed the root system for type BC and the non-reduced type. And then in McDonald theory, I only have Q and T, and as Nakajima-san has mentioned earlier, the parameters C1, 2, 3, 4 that he listed are what are usually called A, B, C, D. It's the specialization of those parameters that gives me these affine root systems. So, okay, I have a family of commuting McDonald Q difference operators. McDonald wrote them down. So there's no, of course I can choose a different family, sort of algebraically dependent. But they have nice eigenvalues, so I will just stick with McDonald's choice. But for Koornwinder difference operators, we have the Koornwinder operator, and the higher commuting operators were written down by Van Gien, but also McDonald wrote some of them down for some of the roots. And then there's I actually have to add more ingredients to this, so there's the operators written down by rings. And depending on these parameters, I have to choose a different family of commuting operators to solve my problem. So this is why I mentioned all these different versions. The elementary symmetric functions in the McDonald side of things, the type A, they're just the elementary symmetric functions. So an elementary symmetric function in the variables S1 through Sn is just the usual elementary symmetric function. And on the C side, I have it's the extended elementary symmetric functions in S and S inverse. So the VAD root is the C-type VAD root. So, for example, the first one is the sum of all the SIs and SI inverse. So that's the sort of comparing the two sides. This is well known to everybody in this room, so I don't have to harp on it. And then I have these functions, phi I don't remember whose notation this is. And anyway, McDonald's function, in the McDonald side, it's this rational function that involves the roots of type A, and on the Koornwinder side, it's slightly more complicated rational function that it explicitly depends on Q. So here, alpha alpha runs over the parameters A, B, C, D. And I have to take the product over these. But this involves the BC type, which is okay. So then the first McDonald operator is just the sum over this rational function times gamma I. So gamma I take this to be the first point. So I'm going to have two quantum tori, two n-dimensional quantum tori. So gamma is the Q difference operator in X. So if I multiply xj by gamma, by gamma I, then it multiplies xi by q and does nothing to whatever x is. So this is a Q difference operator in X, that's the point. And then on the Koornwinder side, so I take the following, I take a normalization. So earlier I asked Nicodemus on how his d acts on 1. This d acts on 1 triggered it, so multiplies by 1. So the constant is chosen this way, and this minus 1 is the standard minus 1. So this is the Koornwinder operator. So here I have to sum over the c type. Is it better? Oh, it's a second generation. I'm learning on the fly here. Okay, so I symmetrize over a C-type fiber. Okay. And then, as we know, the first equation with D1 uniquely determines the solution to this if you choose sometimes. So the solution, the eigenfunctions P lambda, are uniquely determined by the first eigenvalue equation, and then uniquely determined means, well, I have to choose what I want this eigenfunction to look like. So the domain of analyticity, so I'm going to expand it. I'll be more specific in a second. And also there's a notion, the question of normalization. So both of these I'm going to play with. Okay. But in any case, in both cases, this function phi I, this rational function, can be expanded as a series. This is the choice I'm making. In x to the minus simple roots of whatever the algebra is, either type A or type BC. Any questions? You know I have a full palette because precedence is set. All right, so Shirishi-san was the first person who showed this to me, but I understand that. So Shirishi and Nomi have this for the simpler cases, maybe. And then Stockman discusses basic Hurwitz-Chandra series, and then you can see it elsewhere. You choose a solution like this. So I'm going to parameterize, just to go back, remember I have this lambda. All these functions, they depend on lambda. And I didn't say what lambda is. So you choose to parameterize lambda via the variables s. And here, did I write it down here? Sigma is equal to A, B, C, equal to it's just one parameter. So I choose to parameterize lambda by s, and I choose to parameterize x by mu. And so out front here, I have a factor, explicit factor of q to the lambda dot mu. Lambda and mu are vectors. And then I expand in x to the minus beta, where beta are summed over all the positive root lattice. And the coefficients, C beta, they depend explicitly on S, don't depend on X. And if I choose this, then because I said I could expand any of the difference operators in terms of powers of x to the minus alpha I, the difference equations have a unique solution. They are a triangular system for the coefficients. You can compute them one by one for each one of those algebras. Okay. And then if lambda 1 through lambda n are just formal variables, these series of universal solutions in the sense that if I specialize lambda to be integer partitions of this form, then P of x and s becomes a polynomial. The series truncates. And these are all, any of the Koornwinder polynomials and any of the Mcdonald polynomials can be obtained in this way, so these are universal functions in that sense. So this is when lambda is an infinite, an integer partition, and important, the normalization. So the normalization, if you're going to want to get down the Koornwinder polynomials, C0, the first coefficient here, is equal to 1. All this I learned. Yes?
In this case, can you see that these become polynomials in a series? Or
Yeah, you can see that C becomes 0 at some point. So you can say exactly what. So on this side, you can see. But the fact that they're symmetric, that has to do with the prefactor. And then there's duality, or in some communities called the bistructural property. So there exists a normalization C0, which is not the C0 is equal to 1. So I'm going to call it delta inverse of S, such that the universal function is almost self-dual. And so what does it mean? It means, so I wrote down the universal function as a function of x and s in a symmetric way. It's actually symmetric under exchange of the formal variables x and s, if you choose this normalization. So everything is tuned to that. And this star, well, star means there's some involution on the Koornwinder parameters, which I'm sure most of the people in this audience know better than me. And the star means the function with respect to those new variables. And this function delta is important to compute. So it exists, and it's not exactly the McDonald delta that was, I think I saw some people writing down this delta plus. It's not exactly the McDonald, it's not the McDonald delta plus, but it's closely related to it. So in type A, it's just phi, it's essentially controlled by a function phi that we introduced earlier. So in type BC, it's a little bit more complicated. But again, you see the same product over the roots of BC type. Sorry, phi is the quantum dilogarithm. So the quantum dilogarithm in this particular lecture is going to be defined as the infinite product. Yeah. K goes from 1 to infinity. I don't even know when I do that.
Don't double tap.
I don't do it consciously. I don't do it on purpose.
Music.
So this is the quantum dilogarithm. And so for me, this is very suggestive. This is an interactive talk. Better? We'll see. Yeah, so I think that I don't have to say this. So sometimes I talk about this Peary rules and duality, and people look at me blankly, but I think in this audience, everybody knows about duality. And Peary rules, so if I start out with the eigenvalue equations, change variables x to s, so I just rewrite these equations. Sorry, this epsilon here, it's almost but not quite the eighth elementary symmetric function of either A or BC type. And then I use the fact that P is self-dual, so I get this, and then I also change right hand and left hand sides. Then I get that, so if I rewrite this, if I actually convert this to honestly the elementary symmetric function, then the right-hand side of this equation becomes some Q difference operator HA of S, and HA of S is a Q difference operator in the variables S, which then becomes what I call the Hamiltonian. So the Peary operator, they're commuting operators because the McDonald operators are commuting operators. And the Q difference operators, but now in a new quantum torus, which is S and the operator that multiplies SI by Q. I'll call it T as opposed to gamma. Okay, so the idea is to first of all, I need to construct these Q difference operators dA of S, the higher Koornwinder operators, whose eigenvalues are elementary symmetric functions. Okay, so if I pick the operators provided, so I combine the operators provided by Vantian, McDonald, and very important Rain. It really took us 2 years to figure this out. if I do a judicious picking, then I can find the n commuting difference operators that do what I need. This is important for me because I'll explain why in a moment. So this choice of operators is important. All right. So the corollary is that, well, I can solve this equation in the same way that I solved the O'Donnell equation, and I come up with a series solution. But now this is a Q difference operator in S. It's a triangular system in the coefficients. But the coefficients now are functions of x, and the expansion is in terms of x to the minus beta. So beta is an element in the positive root lattice. And so this is a series, and it's not obvious, for example, if I specialize now S, why this is going to truncate. It doesn't obviously truncate. But it should be equal to the other series. Okay. So I need to specialize the parameters for each grid system, and this is a table you may or may not have seen before. I suspect none of you have seen this table. It's complete glory, but if you have, let me know. So for each of the BC type grid systems, can you see the right, actually? Okay, because I can't from here. In this specialization, A, B, C, and D are just powers of Q and T, and the only time, so the root system R and the root system R star, that's McDonald's notation. So McDonald didn't use Katz's notation because his name is McDonald, so he used McDonald's notation. R and R star are finite root systems, and I believe after averaging all the McDonald papers, probably I should call R and R star this and take in the last case. So the last case is always the outlier, A2 and 2. Okay, so this is not a reduced root system. And the only time when R is not equal to R star is untwisted BC, right? So you can forget about star in all other cases. All the other systems are self-controlled. Okay, so as an example, so the functions, I'm going to call these phi's, the coefficient in the Q difference operator, and the Koornwinder operator phi. They specialize in some of in the rational functions, some of the terms cancel. So in type D, it's just this. Again, you see that it depends on the type D root system. So this gives me a hint that at least this column is good. And in type C, it specializes in this way. Yeah. So I have the type C root system in there. Okay, so any comment about my table are welcome. And the parameter sigma that I introduced earlier is always some power under this specialization. So after this specialization, I'm going to call the specialized operator as Koornwinder McDonald operators in different diffusion gradient systems. Okay, and then this delta, this function delta, is also specialized, and it becomes a product over well, essentially half of the affine root system. So this particular half that I show here. And somehow this is a half of the affine root system. So I know that this is the right affine root system. And the remark here is saying the following. So if you find the universal Koornwinder function, and you specialize it at lambda an integer partition, you get a polynomial. But after you do this specialization of the parameter, then some of the dominant highest weights are parameterized by, say, half integer partitions, or the last part of the partition is negative. Then those two specialize to the polynomial. So I get more Koornwinder polynomials for these systems. So I get the symmetric polynomials for any R partition. So yeah, this is about the choice of commuting difference operators. So I construct these Ds using the constructions of Eigen, McDonald, and Reines, such that their eigenvalues are the relevant elementary symmetric functions in S and S inverse. I need to do this before I take any limits, and I need all n of them. And then by duality, multiplying by the elementary symmetric function gives me some Q difference operator HA of S. Okay, so now what I do is I take the Q Whittaker limit. Q Whittaker limit is usually T goes to 0, but because McDonald or Koornwinder polynomial has some symmetry, Q going to T inverse Q inverse, we like to take the limit T going to infinity, just for historical reasons. And then the eigenvalue equation, so before I said you could just take the first eigenvalue equation and solve for the universal solution. What happens to the eigenvalue equation in this limit? Well, the elementary symmetric function in S, because S explicitly depends on T, so let me just remind you, Si is sigma T to the n minus I Q to the lambda I. This explicitly depends on T, and so an elementary symmetric function in S is not going to stay elementary when I take the limit down. It's not going to stay symmetric. So when I take this Whittaker limit, so only the dominant term remains, and I claim that if I clean up everything, it's just Q to the omega A star, omega A, the fundamental weight of R star, which is usually R, but not always, dot lambda, so that's the term here. So the Q Whittaker limit of the eigenvalue equations becomes this. So the Q Whittaker limit of the McDonald function, I'm going to call the Q Whittaker universal function. In the limit, nothing much happens to the Koornwinder or McDonald operator. It's still a rational Q difference operator. But notice that instead of an elementary symmetric function here, I get a monomial. It's really simple. On the other hand, what happens to the Peary rules in this limit? Well, E of x, that officially doesn't depend on T, it just goes to E of x, the elementary symmetric function. But the Peary operator drastically simplifies and become Laurent polynomials. So the right-hand side of both of these equations is much simpler than the Q Whittaker. That's my statement. Okay. So I'm going to call this limit of the Peary operator Hamiltonian, so the quantum characteristics for the Hamiltonian in the variable lambda. I wrote down one example. So they're different for each of the root systems. I had to specialize to each of the root systems because remember, the variables A, B, C, D, they depend on T, so how I take the Q Whittaker limit is going to make all the difference in the world. So for type C, the first Hamiltonian, if you look at it, so it has T and T inverse, and then it has Q to the lambda dot alpha A. That's the same. So it's a Laurent polynomial in the variables T and Q to the lambda. And T and Q to the lambda are my second quantum torus. So Tj Q to the lambda I one is by Q to the lambda J. Right. But notice that the Cn Hamiltonian, because R star of C of type C is B and R star of type B is C. This is the root system of type Bn, so not C. Okay. So I call these Hamiltonians, so I must have some discrete evolution in mind that commutes with its Hamiltonians. So the Hamiltonians are conserved quantities with respect to some discrete evolution. So what is this discrete evolution? So my claim is that before I take the limit, okay, the McDonald operators are elements in the functional representations of the spherical data, or the Koornwinder operator. And so there is an SL2, almost SL2 action acting on the spherical data, or on the data itself. And I'm going to call the generators T plus and T minus. So upper triangular, lower triangular, just use to generate SL2s. And one of those two actions survives in the Q Whittaker line. And this action is, let me call it tau plus. I haven't said what tau plus is. Okay, here's tau plus. It's upper triangular. Let me just call it that. And so this action, so here's how you draw it in type A, right? So you have sort of this is the elliptic Hall algebra picture, cohomology picture. You have these operators, and here you have the elementary symmetric functions on the x-axis, and the McDonald operators on the y-axis. And then tau plus acts on this plane as you would expect. So it commutes with the x-axis, so it commutes with the elementary symmetric functions in x, but it does something to the McDonald operators, the Q difference operators. It doesn't commute with the Q difference operators, so it's a shear operator. Okay? Is familiar to everybody? All right. I have a very enthusiastic listener in the front, so I'm assuming everybody else is nodding, and so I assume everybody's understanding. Okay, so this star has to do the, okay, sometimes it's only SL to 2Z or something like this, but I'm not going to, because you only give me 45 minutes to talk, I'm not going to actually explain the exception in this case, but those are the ones that give you the headaches. All right. Tau plus acts on the functional representation of the spherical Dachau by the adjoint action of gamma of x inverse, where gamma of x is the Choroidnet Gaussian. So gamma of x is the exponential of the log of x squared over 2 log of q. This is a very nice operator. Maybe you're not used to it. It's very simple how it acts on the functional representation. It acts on x by commuting it. This is just a function of x. It's not an element in the spherical Dachau, but it acts on the spherical Dachau. It's in some completion of the spherical Dachau. Obviously, this commutes with x. Right? It doesn't do anything to x, but the Q difference operator in x it doesn't commute with. But it doesn't badly not commute with it. What it does is it takes the Q difference operator in x and multiplies it by x, essentially. So actually, the action of such a thing is very simple. If you don't care for such a Q exponential, then just look at this action. Then it acts on the McDonald operators in a very simple way. For example, if I have some function of x here, some function of x, right? And I act on it with tau plus, then it just multiplies this gamma I, well, probably with some power of q, but apart from this power of q, it just multiplies gamma by xi. So the action of this tau plus on the McDonald or Koornwinder operators is very simple. And this theorem, for the rest of the stuff, this is all I want to say. The tau plus action on the McDonald or Koornwinder operators in the Q-Whittaker limit are solutions of the quantum Q system from type G, if I choose these operators correctly. In fact, what I did was I started out with a Q system, I quantized it, I will say in a moment what that is, and I looked for the solutions for the Q difference operator to realize this system. So, what is a quantum Q system? This is a system of mutations, quantum mutations for some A-type cluster variables. So Q systems themselves, there's something that came out of the paper of Kirillov and Oshetikin, and then Hatayama and company wrote down Q systems for any one of the affine algebras that I mentioned, and then the quantization has to do with the observations that these are mutations in the cluster algebra, and a cluster algebra has a canonical quantization. These are the quantizations. So what does it mean? It means that, so what are Q systems? They're recursion relations for characters of finite dimensional representations of the Yang-Yan of G. And then I Q deform these recursion relations. That means that instead of characters, I get something where some variables which are non-commuting variables, so they're no longer interpreted as characters. So there are the words K theory and so forth, but I don't speak that language. So the statement is that if you take the Koornwinder McDonald operators in type G and tau plus translate them, then I get some sort of creation operators for, well, generalized Q-Whittaker functions or fusion characters in the sense of Pagan and Loktev. And those creation operators for generalized Q-Whittaker functions satisfy quantum Q systems. So I'll write this down. So here's what one way to define a quantum Q system. I'm not going to define cluster algebra, but if you speak cluster algebra, so some of the people in this audience speak cluster algebras, I thought this cluster algebra is defined by an exchange matrix. So the exchange matrix is just 2n by 2n matrix that depends on the Cartan matrix for R, the algebras R and R star, the McDonald group systems. So in the untwisted case, you just take the Cartan matrix for R star, put it up here, so it's just CR transpose, CR down here, and a tiny little bit up here. And for the twisted cases, this is due to Harold Williams, you just take Cartan matrix with A bar transpose. So in all of those, so in this case it's a skew-symmetric matrix, in this case it's a skew-symmetrizable matrix. And if you really want to know how to define the cluster algebra, so it's not the entire cluster algebra I'm interested in, just an integrable direction of mutations in cluster algebra. And this integrable direction, well, it starts out with some seed variable a sub k. So A-type cluster variables, which consist of variables called QA, comma, K, or 2K. So here T is 1 or 2, depending if I'm talking about a long or a short label. And also QA, TK plus 1. And here A goes from 1 to the right of R. And quantum cluster algebra, I also have to define the commutation relations between these variables. So the variables that don't commute in this seed variables, there are two rank R variables here, are just neighboring variables, and they commute with this matrix Q to the omega A star omega B. So everything is defined by the McDonald group systems R and R star. So I have Q commutation relations. So the variables in the first seed are sort of, they almost commute. And the discrete evolution is, if I translate Q A K, I mutate it. So I translate K by 2. So K is the time direction, the direction of evolution here. So the claim is that this can be realized by a sequence of mutations. And if I consider this as a discrete time, then the quantum proto-Hamiltonians that I defined from the Koornwinder operators commute with this evolution. So they're Hamiltonians for this evolution. Okay, here are examples of Q systems and quantum Q systems. So most Q system relations just look like this first relation here. So this is actually all you have to know about them. So they're a Plucker relation. So QA k plus 1, so Q at time k plus 1. A is the root variables. Times QA k minus 1 is, it depends only on the variables at time k. So it's QA squared, and then minus QA plus 1, QA minus 1 at time k. So those are the neighboring dating tables. So this is a Plucker relation. When you quantize this, you get a quantum Plucker relation. So in fact, I wrote this down in a very innocent-looking way, but in fact, these two variables, they don't commute and they don't Q commute. So if you take them, multiply them in this order, then the quantum relation looks exactly the same. These are non-commuting variables, and the only thing is you have to multiply by Q to the omega A, star omega A. That's usually the prefactor here. And then, in general, so this is in type A, and almost all of the roots in the other types. So the roots that look like type A. This is the time evolution. So this is a two-step time representation in type AK. It's a discrete evolution. In type D, okay, so at the end of the Dayking diagram here, you have some other neighbors, and so you're going to have a cubic relation. But in type D, the quantization of the Q system, it just looks like this. So you just take, for the second term here, you just take the product over the neighbors in the Dayking diagram. And well, how is the non-simply laced type different? The non-simply laced type looks exactly, again, the same as type A and type D. But at the end of the thinking diagram here, when I have to so if I'm at the end of if I'm looking at this guy and I want to know what's over here, or if I'm looking at this guy and I want to know what's over here, time actually moves twice as fast for short roots as it does for long roots. What do I mean by short roots and long roots? Well, okay, for type B, it's obvious this is the short root. So the time evolution in type B, it travels twice as fast. What I mean by short roots and long roots is the same. Short labels and long labels is the same as what you usually mean, except in this algebra 8, 2, and 2, which is always exceptional. So these are the affine systems I'm talking about. And you just ignore the blue label here, which is the affine label, and the orange labels are the short labels. So time for short labels moves twice as fast. So here's my claim. The Q difference operators, T, A, TK, are just the T plus to the K action on the McDonald-Koornwinder operators. And then here, T is equal to 2 for short roots. Otherwise, just ignore it. Satisfy the quantum Q system. So that is the tau plus translated McDonald operators or Koornwinder operators are in the functional representation of the quantum Q system. And so because I know that these are actually in the spherical Daha for whichever relevant type it is, now I know what the quantum Q system is. It's just relations in the Q-Whittaker limit of the spherical Daha. And then as a result, creation operators for Q-Whittaker functions, or Q-Whittaker polynomials, take the Q-Whittaker polynomial corresponding to the partition lambda and act on it by dA1, and that will give you Q-Whittaker function of type lambda plus omega. So I'm going to say some things about the proof because that's probably where you know some of the elements. So the proof of these statements, again, people used this notion here before, I think yesterday, of the Fourier transform. If I have, so Q-Whittaker functions are a complete set in the following sense. If I have a set of operators di, Q difference operators in X, acting on the Q-Whittaker functions as some Q difference operators in lambda, so this is not an eigenvalue equation, it's just a Q-Whittaker transform. Then if this di of X satisfies some equation, some algebraic relation R, then the Q-Whittaker transform satisfies the same relation with the opposite multiplication. So if I want to prove something about the operators di of X, I just have to prove the relations for the Q-Whittaker transform. And somehow this is really easy to do in this limit. Here's what I'm going to do. I'm going to define the d hat, the Q-Whittaker transform of my Q difference operators. So Q difference operators in lambda and so T and lambda. And then I'm going to define them from the quantum Q system with the opposite multiplication. And then I'm going to prove that they're in Fourier transform. That they're Fourier transform of these transform McDonald operators. Okay, so here's my definition. For dA0, I'm going to choose the eigenvalue of the McDonald operator in the Q-Whittaker limit. So remember I said it was just a monomial. It's just Q to the lambda omega A star. So this could conceivably be the Q-Whittaker transform of the McDonald operator. For the first operator, dA1, I'm going to choose some element in the quantum torus in lambda and T that Q commutes with dA0 hat in the right way, given by the commutation relations from the quantum Q system lecture. So the commutation relations should be given by Q to the power omega A, omega B star. Well, actually, minus omega A, omega B star. But I'm choosing the opposite multiplication. So if I choose it in this way, this satisfies, so this is the simplest choice such that it satisfies the correct commutation relations. And then I have some other criteria. This is what I want for the first. Okay. Remember, the quantum Q system, the Q system is a two-step recursion relation. So if I have two initial data, this and this, and I say that d hat AK is given by the quantum Q system with the opposite multiplication, then it's uniquely determined given this initial data. So I can recursively solve it. And moreover, these are just monomials. So because this is a quantum cluster algebra relation, and so I know that dA hat is just going to be another Q difference operator. It's going to be a Laurent polynomial in these two sets of variables. Here, quantum cluster algebras. So I know it's going to be a nice Q difference operator. Remember, T is a Q difference in lambda. And so all I have to prove is that D hat is the Fourier transform of the translated Bernoulli operator. Everything up to now is just a definition. So the theorem, for each root system, this definition, it gives me a unique element, which I call it suggestively gamma hat of G, a Q difference operator in lambda. Again, not in the spherical data, but in some sort of quantum exponential, such that the Q system defines for me this operator so that gamma, the adjoint action of gamma hat, acts on dAk by translating k by either 1 or 2, depending on whether it's a short or long wave. What this is you just have to check the first couple of steps. And actually, you will see that it defines for you a Q difference operator, computed explicitly. I give an example here of what it looks like. It's a quantum exponential. But for each Q system, it's going to be a different operator. This is from the form of the Q system. All right. So, for instance, I gave types A and D. Gamma hat is, well, it's a Q exponential or quantum dilogarithm in T times a quantum dilogarithm in lambda, in Q to the lambda. So this is a product of quantum dilogarithm. There are many identities for quantum dilogarithms, and there's an infinite number of ways of writing this expression. But this is one expression that you can write down for it, and then you have to try and make identification. And here, alpha I are the simple roots of the system 1. Now, I'm sweeping under the rug 2 years of confusion about how to treat short labels, but I'm not going to say anything about that. So it gets much more complicated when I have short labels. But essentially, this is how it looks. And then you check. So we derive quantum total Hamiltonians for each root system. We didn't write them down, but we derive them. You check by hand that these gamma hats that you get this way actually commutes with quantum total Hamiltonians. So it gives you some hope that you've done something right. So by explicit computation. And then the theorem, so using this fact, you can prove that gamma hat is the Fourier transform of the Choroidal Gaussian for each root system. So the hat looks different for each root system, whereas the Choroidal Gaussian always looks the same. So that is when they act on the Q-Whittaker function, gamma hat acts the same as gamma. The proof goes like this. The solution to the Piari rule is unique up to a multiplicative function of x. Remember, the Hamiltonian is a Q difference operator in lambda. It doesn't see functions of x. So you act with, and also gamma hat, I said, the translation operator, commutes with the Hamiltonian. So if I act with, and it commutes with an elementary symmetric function because gamma hat is a Q difference operator in lambda. It doesn't see x. So it commutes with the elementary symmetric function in x. So if multiply the Peary equation by gamma hat, then gamma hat times the Q-Whittaker function is again an eigen, or it satisfies the same Peary rule. So it must be proportional to up to a function of x to the original solution of the Peary equation, which was a Q-Whittaker function. Okay, then you just use the universal solution to the Q-Whittaker function, which remember was a series expansion S for Q to the lambda. And just compute what this function f has to be, and when you compute what this function f has to be, the result is that it's the theorem Hamilton. So there was a limited number of calculations here. For each root systems you have to compute this separately, but it's a limited number of calculations. And because of this, this shows, I don't want to go over this, but so dA hat is in fact the Fourier transform from the time translated Koornwinder McDonald operator. So I'm going to skip this proof, but it's sort of the obvious proof. Therefore, I conclude that the quantum total Hamiltonians are the conserved quantities with respect to this time evolution, gamma hat or the Q system evolution for each G separate. I'm flying by these. Yeah, this is just a remark. This expression for the theoretic Gaussian, I claim, is just so it's just a product of quantum logarithms. To see why it commutes with the Hamiltonian, well, the Hamiltonian, remember, when you multiply by the Hamiltonian, it's like multiplying by an elementary symmetric function in x. Well, so if you look at the theoretic Gaussian, you can re-express it in terms of, well, it's the elementary symmetric function of type B. So it's a Q exponential of the sum of these elementary symmetric functions. So it's a generating function for these elementary symmetric functions. So it gives you an idea, and this is how the total Hamiltonian acts. So it gives you an idea of why it should commute with the Hamiltonian. And one last remark. So someone mentioned Baxter operators. I'm not going to use the word Q operator. So yes, Baxter operators are in fact the true generating functions for the quantum Hamiltonian. So this is following a paper of Shapiro and Schrader. So they look at the type A cluster algebra. So in type A, the quiver for the cluster algebra looks like this white thing over here. If you just change that quiver slightly, you add one more node, and you put a spectral parameter on that node, and whatever variables need to be in order for this quiver to have the right polarization. So this is like the A-type Q system cluster algebra plus one node. And you start doing a sequence of mutations that look like this. You follow me. It goes like this. This is when you do a mutation in a quantum cluster algebra. It's like taking an adjoint action by the Q logarithm. And the Q, so it becomes a product of Q logarithms depending on the spectral parameter U. And this product, for them, this is what they call the Baxter operator. So there's some limit of a Baxter PQ relation which is satisfied by this. If you evaluate when U is equal to 1, you will in fact get my operator, gamma hat, which I said was the time translation operator. So in fact, it's an evaluation of the Baxter operator for type A. Okay, so then you can define the Baxter operator for the other types in a similar way, I claim. And so you'll get, well, there are many, many Baxter operators hanging around, but this is relatively nice. So it's an exponential generating function for the quantum total Hamiltonians. And I'm going to stop here. So my chairman is very lenient, but I think it's time to stop. I need to know. Wait. So just to say, okay, wake up, and this is what I said. Quantum Q systems are satisfied by the Q-Whittaker limit of Koornwinder. Turns out Koornwinder was done. How long is it? The quantum Q system algebra is essentially the spherical data in this limit, in the Q-Whittaker limit. Somebody yesterday gave a talk about exceptional type higher Koornwinder type operators, so, or McDonald operators. So that is completely open, and you're perfectly welcome to try to do this, to play the same game with the operators that were listed yesterday. And then in front with Schrader and Shapiro and Francesco. So even if you don't take the Q limit, there is some of the structure remaining. So I tapped it and I said, okay, there's a quantum cluster algebra structure. There is some of this cluster algebra remaining. So I augment my quiver just a little bit more. I put it on a torus. And these McDonald operators and their translations, they're now not cluster variables. They're in the upper cluster algebra of this augmented quiver, at least for type A. We don't really know what to say in other types. Okay. Thank you.
Thank you very much. Questions or comments?
So you consider the Q with the current limit. I was wondering whether you have a Koornwinder operator itself can be regarded as a quantum Q system.
Okay, I think this is what I said very briefly. So for finite T, what happens? Okay. Then in finite T, the relations that are satisfied, so this sort of the spherical Daha relations, it's not a cluster, it's not a quantum cluster algebra, but the Koornwinder operators themselves at finite T and their translations are some finite, they're polynomials in cluster variables. Or if you look at the cluster algebra on a torus instead of what I wrote down, you just extend it a little bit, then what you can say about those operators, they're elements in the upper cluster algebra. And the sort of the mapping class group elements are also the sequences of mutations in this cluster algebra. So this is a work in progress.
Any other questions?
Is it possible to take Q with our limit without specializing ABCD?
Right. So you can't because the specialization A, B, C, D depends explicitly on T. And so what happens to the operators themselves, their structure actually changes depending on which power of T you had. So in fact, this is why I had to first specialize and then take the limit. Of course, you could take the limit without doing that. You will get one structure. I don't know what it will be. It will not be any of those Q systems.
Any other questions or comments?
I have a comment about that actually. Apparently that's too slow.
No, that was the agreement.
Yeah, I see. Related to that comment, I think that there's a way that we use it in the elliptic case, but Buckavanagalt and I sort of developed a way of exploring the entire space of such limits. And so basically what you're going to find is that there's going to be some piecewise linear, the decomposition of the possible ways in which A, B, C, and D depend on T will be some piecewise linear thing. And then there's going to be, each one of those is going to be, each region there is going to give you a different limit. The only complication is that the piecewise linear decomposition may depend on the number of variables. So there's some potential complications there. But in principle, this is
So one could try to explore it.
Yeah.
Any other questions or comments? So let's have speaker again. So next talk will start at 4:30. We have a 15 minutes break.